Okay, let's just imagine for a second. Picture yourself as an engineer, and you have to build one single component.
Right.
This one piece of metal has to endure two completely, well, physically impossible extremes.
And that's the key, right? They seem impossible to combine. On one hand, you have the vacuum of deep space. We're talking near absolute zero.
Something like 4 Kelvin.
Exactly, 4 Kelvin.
Mm.
Most metals, even really high-strength ones, they just become incredibly brittle at that temperature. They'd shatter like a glass ornament.
Right, like Captain America frozen in the Arctic ice, just totally solid.
Yeah, that's a perfect way to put it.
But then that exact same component has to immediately withstand the kind of heat you'd find in, I don't know, a Star Trek warp core firing up.
Or a fusion reactor. We're
Yeah.
talking scorching, white-hot industrial temperatures, up to, say, 1673 Kelvin.
That is a staggering range. What is that, 670 Kelvin difference?
It is. And in material science, that has always been the ultimate trade-off. It's a fundamental barrier.
You design for cryogenic strength, you lose heat tolerance. You design for heat, and it gets weak or brittle when it's cold.
It's been an insurmountable problem. Until now.
But today, we are diving into a discovery that seems to have completely erased that trade-off. Welcome to the deep dive.
Today we're exploring a breakthrough material, a refractory high-entropy alloy, or RHEA, that doesn't just survive this wild temperature spectrum.
It actually thrives. It functions perfectly across the entire range by sort of automatically adapting its internal structure.
The core of what we're talking about comes from this really remarkable piece of research published in the journal PNAS. This was in January of 2026.
And the title is a mouthful, but it says it all.
It really does. It's called Self-Adaptive Dislocation Morphing Ductilizes a Refractory High-Entropy Alloy Across an Ultrawide Temperature Spectrum.
That title alone just hides an incredible story of ingenuity.
It does. And, this was a huge collaborative effort. The corresponding authors were Qing Zhang, Hongbo Guo, and Shiteng Zhao from Beiyang University and Tianmushan Laboratory.
And they were working with a big name in the field.
A very big name. Robert O. Ritchie from the University of California, Berkeley.
So our mission today is to really unpack their central finding. How does this one alloy, and we'll call it the NB40 alloy for short.
Please. Its full name, NB40T25Ti15HF15ZR5, is not exactly catchy.
Right. So how does this NB40 alloy achieve both exceptional strength and, crucially, exceptional ductility from 4 Kelvin all the way up to 1673 Kelvin?
And the secret sauce they found, the mechanism, is this concept of self-adaptive dislocation morphing. It's basically proof that you can design a material that changes its fundamental strategy for dealing with stress depending on the temperature.
It's like the alloy has an internal toolkit, and it just knows whether to pull out a hammer or a wrench depending on if it's freezing or, frying.
That's a great analogy.
So let's set the stage. What's the core dilemma here? Why do metals normally fail at these extremes?
It all comes down to their crystal structure. When you cool a conventional metal way, way down, its atoms have less thermal energy. They can't move around.
The whole lattice just locks up.
It locks up. And when you apply stress, it can't bend or stretch plastically. It just cracks. Catastrophic failure. That's the classic ductile to brittle transition.
Okay, and what about the other end? The heat problem.
Heat is the opposite problem. It gives the atoms too much energy. The bonds between them soften, and the material loses its structural integrity. It just starts to slowly deform under pressure.
So it creeps.
It creeps. And even our best materials today, the nickel-based superalloys in jet engines, they suffer catastrophic embrittlement below 77 Kelvin. They're a non-starter for true cryogenic applications.
So scientists started looking at these refractory high-entropy alloys. The refractory part means they have really high melting points, which is great for heat, but what was their Achilles heel?
Ductility, especially when they got cold. They were fantastic at resisting melting, but they were still prone to that same brittle fracture at low temperatures. They had the strength, but no give.
And that's where the NB40 alloy, the star of this paper, comes in.
Exactly. It's this 5-element alloy, and the key thing is it maintains a specific crystal arrangement, a body-centered cubic or BCC structure across that entire temperature range.
Okay, so walk us through the performance. What were the wow facts that made the research team know they were onto something huge?
The data is just staggering. At room temperature, about 298 Kelvin, it's seriously strong, a yield strength of nearly 800 megapascals. But more importantly, it has great ductility, about 25% fracture elongation.
So it's strong and tough, a great balance.
Fantastic balance for normal operating conditions.
Ugh.
But then you go to the extremes.
Let's go to the cold first. 4 Kelvin.
At 4 Kelvin, that literal freezing cold, it retains 10% tensile ductility.
Now, 10% might not sound like a huge number compared to 25.
But it's revolutionary.
Right.
For a refractory alloy at that temperature, it's unheard of. This retention of ductility means you see this thing called necking, where the material draws thin before it finally breaks.
So it stretches instead of just snapping?
Precisely. The authors emphasize this point. It shows complete absence of the ductile to brittle transition. It stays tough enough to function.
Okay, so now we have a component that can handle superconducting temperatures. Let's flip the switch. Crank the heat up to 1673 Kelvin. What happens?
This is the wildest part. Instead of softening and falling apart, the alloy enters a state of superplasticity.
Superplasticity.
The elongation just soars. It reaches an incredible 250%. Think about that. The same piece of metal can operate next to a cryogenic magnet, and then you can heat it up until it glows and stretch it 2.5 times its original length.
That is it's a revolutionary level of versatility. You no longer have to choose.
You don't. And the critical insight from their X-ray diffraction work was that this isn't happening because the material is changing its chemistry or its basic crystal structure.
It stays as a single-phase BCC structure the whole time.
The entire time. The secret is all mechanical. It's about how these tiny atomic-level defects inside the crystal manage the stress.
Okay, so we have to talk about those defects. This is the heart of the self-adaptive morphing, these things called dislocations.
Exactly.
Right.
Dislocations are just tiny imperfections, line defects, in the otherwise perfect crystal structure.
Yeah.
And they are the reason metals can deform. When you apply stress, these dislocations move and multiply.
They're the gears of the system.
They're the gears. And the genius of the MB40 alloy is that its complex chemistry creates this intrinsic temperature-responsive evolution in how the dislocations behave. It has 3 different strategies in its tool belt.
All right, let's break them down. Let's start with the toughest challenge. Mode 1, the cryogenic kink twin strategy. How does it stop itself from shattering at 4 Kelvin?
So at those ultra-low temperatures, there's almost zero thermal energy. A certain type of dislocation, a screw dislocation, becomes very long, straight, and just stuck.
Yeah.
Pinned.
Okay.
They can't move enough to relieve stress, and that's what would normally cause the metal to just fracture instantly.
So how does the alloy cheat? What's its trick?
It has a 2-part trick. First, it forms these localized kink structures in those pinned dislocations. You can think of a kink as a tiny internal bend that lets the dislocation hop forward just a little bit.
A quick fix to release a bit of stress.
A quick fix, yeah. But for the really impressive ductility below 77 Kelvin, it activates a bigger strategy. Deformation twins.
Twins, you said that before. What are they?
They're essentially mirror-image crystal structures that suddenly form inside the material. They create a whole new pathway for deformation to happen.
And the researchers found something that helps this process along.
This is the coolest part. Using high-resolution imaging, they discovered a temporary transitional structure they call the omega phase.
The omega phase.
It acts like a lubricant for the twinning process. It triggers the twinning through this multi-step atomic shuffle that massively lowers the energy needed. So this combination, the kinks plus this lubricated twinning, completely suppresses brittleness.
That is just incredibly smart design at an atomic level. Okay, so that's the cold. Now let's go to room temperature. Mode 2. The ambient edge screw strategy. How does it balance that high strength with the 25% ductility?
For this part, they use some really cutting-edge tech. In situ high-energy X-ray diffraction at the Shanghai Synchrotron Radiation Facility.
So they were watching the atoms rearrange in real time as they stretched it.
In real time. And what they saw was this beautiful sequential activation. The initial stretching, the first bit of plastic flow, is dominated by what are called edge dislocations.
And those are different from the screw dislocations.
Yeah, you can think of the edge dislocations as the fast, highly mobile frontline workers. They move quickly and relax the initial local stress.
So the fast ones go first to absorb the shock, then what?
Then, as the strain builds up, the slower, more sturdy screw dislocations start to activate in sequence. These are the heavy lifters. And their activation makes the internal structure more and more complex.
Wait, so making the structure more complex and tangled up actually makes it stronger?
That's the magic of work hardening.
Yeah.
This sequential evolution means the material gets progressively harder to deform. The growing jungle of screw dislocations creates internal resistance, and that's what gives you that perfect blend of high strength and good ductility.
It's like it starts in a low gear and then shifts to a higher, tougher gear to bear the load. Very efficient.
Exactly.
Okay, final turn of the dial. Extreme heat. Mode 3. The jog junction strategy that leads to that crazy superplasticity.
Right. So at 1073 Kelvin and above, thermal energy is everywhere. Dislocation mobility is hugely enhanced, and as they move, they start forming these little deviations from their path called jogs,
Jogs, little hiccups in the structure.
tiny hiccups. But when these jogs on different dislocations interact, it's crucial. They lead to the rapid formation of stable junctions. This is where two dislocations essentially merge to form a third, more stable defect.
So it's building up this complex internal network of defects. Why doesn't that just cause it to fail?
Because these junctions rapidly connect to form these huge extended dislocation networks and subgrain boundaries. And the accumulation of all these networks drives a process called dynamic recrystallization.
Dynamic recrystallization. That sounds like the material is rebuilding itself while it's being stretched.
That is precisely what it's doing. The microstructure is constantly renewing itself, on the fly, releasing all the built-up stress. This process is what allows the material to flow like a thick putty, enabling that mind-boggling 250% elongation without breaking.
It's actively self-repairing its internal structure under extreme heat and stress.
Yeah, and that really challenges conventional metallurgy. The thinking was that dynamic recrystallization was really only dominant in materials with what's called low stacking fault energy. This NB40 system is a high SFE alloy, but they proved this mechanism is what's driving the superplasticity.
So the versatility of the single alloy is it's a true feat of engineering at the defect level. Let's try and summarize the big takeaways here.
I think the biggest takeaway is this idea of a self-adaptive design. We now have a clear mechanistic roadmap showing that a complex alloy can have 3 different sequential deformation modes that are triggered purely by temperature.
Right. First, at 4 Kelvin, you have the kink twin strategy, which uses that omega phase as a lubricant to prevent brittleness.
Then, at 298 Kelvin, room temperature, you have the edge screw strategy. It sequentially activates fast and slow dislocations to give you that great balance of strength and ductility.
And finally, up at 1673 Kelvin, the jog junction and recrystallization strategy kicks in, constantly rebuilding the internal structure to allow for massive superplasticity.
And this isn't just some lab curiosity. The complex chemistry of the RHEA is what stabilizes these atomic behaviors and makes them predictable. The research provides a concrete design principle for engineers.
You can see the applications immediately. Aerospace propulsion, next-gen fusion reactors that need both cryogenic and high-heat components, deep space missions.
It really suggests that the future of engineering isn't just about finding the strongest material. It's about finding the most adaptive one.
Which leaves us with a question for you to think about. If we can engineer an atomic structure that automatically swaps its entire deformation strategy across a 1,670 Kelvin range, what other engineering trade-offs that seem insurmountable right now, like, say, conductivity versus resistance or hardness versus shatter resistance, what if those could be solved by looking for self-adaptive property?
It completely changes how we think about the limits of materials.
It really does. Thank you for joining us on this deep dive into the world of self-adaptive metals. If you enjoyed unpacking this incredible research, make sure you subscribe to stay well-informed on the breakthroughs shaping our future.
We'll catch you on the next deep dive.